been started. And so let's begin the topic of today, which is stellar evolution and remnants. That is, until today, we discussed the stars that we see and we located them on the HR diagram. And most of them we considered as the stationary steady state, that is the period on the main sequence mostly, where the stars will spend the vast majority of their lifetimes, billions of years in the case of stars like our sun. But of course, the universe was not created with the stars as they are today. Stars had to be born, and some of them live out their lives and take the lifetime of the entire universe, but some burn faster, as we saw. The more massive, the heavier that they are, the brighter they burn, the faster they burn out and die. And there are different ways in which stars can die, and we'll discuss some of those and the remnants that they leave behind them today. So as you can see here, also appearing on my background, this is an overview, slight overview of what stellar evolution looks like. All stars basically begin from clouds of gas, which we call stellar nurseries, חדרי ילדים, where they grow the stars until they're born, basically. When a cloud is heavy, cold, and dense enough, that is when the potential energy of gravity in the cloud is strong enough to overcome the kinetic energy coming from the heat of the particles in that cloud, the cloud will clump and there will be some piece of it which will start to condense. Gravity will win over pressure, temperature, etc. As we discussed in the last 2 weeks in stellar structure, that steady state of the star in which it lives out most of its life comes when there's balance, hydrostatic balance between gravity and pressure. So if you want to see something dynamic happen, we obviously have to break that equilibrium, break that balance. And the birth of a star is one of those processes where in particular, gravity is stronger than the pressure. And so the cloud condenses and becomes what we start calling a protostar, something which will become a star. It's a protostar until the moment where when the core gets hot enough to ignite. And then we have hydrogen burning and a star is born. What type of star exactly will depend on the mass primarily, slightly on composition, but almost entirely on the mass. And this is the color scale coming from the surface temperature, which is related, as we saw in previous weeks on the HR diagram, basically to the mass, size, and chemical nuclear processes and what happens in the star regarding energy production. Our sun, a G-type star, and other sun-like stars evolved from a protostar and appear here quite towards the bottom. Below that are red dwarf stars, the smallest type of star which still actually performs stable nuclear burning of hydrogen into helium. Below that we have brown dwarfs, which are basically failed stars. They're clumps of gas which have not reached the required temperature to ignite hydrogen. And so they don't actually burn and produce nuclear energy. So they live out their lives remaining brown dwarfs forever. The more massive stars will end up as a white dwarf when the nuclear fuel runs out. For red dwarfs, it will be a direct process. It will burn until all the hydrogen is consumed and then cool off into a white dwarf. With stars like our sun, there will be an intermediate stage of a red giant, which is when the star finishes its hydrogen, begins to burn helium, grows into a red giant, which eventually runs out of helium as well, and sheds the outer part of the star as a planetary nebula, with the core remaining as, again, a white dwarf. More massive stars can have more interesting ends or destinies. Blue supergiants of various sizes and various masses can go through different types of core collapse supernovae, which we will cover later in the course, leaving behind not white dwarfs, but either neutron stars, which we'll mention today, or black holes, which we will discuss a lot when we talk about general relativity later in the course. And the most massive supergiants can even be so massive that when they finally run out of fuel and die, the explosion completely disrupts and removes all of the gas back into space. So we have different types of final products or remnants coming from stars at the end of their lives, determined by the mass we had in the star during most of its life, itself determined by the mass of the protostar when the star was born. And today we'll talk more about most of these processes, most of this life cycle or evolution of stars. So let's begin. How a star is born. So pictured here on the left is one of those stellar nurseries that I'd mentioned, one of the most famous ones. This is an image from Hubble Space Telescope, so it's an actual optical image. We see clouds of gas in different shades, referring to coming from different optical depths and at different colors. And we see a lot of points where stars are being formed and where stars begin to shine. And this often happens. Stars are not born in vacuum. Stars are born in these clouds of gas, which we call stellar nurseries. This one is close enough that we can actually make out the features with a telescope and see a lot of individual stars shining from that region. How does it happen? Well, as we explained, we have a gas, and that gas can be characterized by different parameters. Most importantly is the mass of the cloud, how much mass we have in our nursery or would-be nursery. The average mass density, the size of the cloud, which we'll mostly take to be spherical, although it's only an approximation, so characteristic length R, the temperature of the gas, and mu, which signifies the chemical composition, as you've seen. Most of the mass in these clouds will be hydrogen in some form or another. So this mu will be determined mostly by the hydrogen fraction, and to some extent helium, and to much lower extents, trace elements of higher elements. Typically, a gas cloud will not be completely homogeneous, as we can see in this image on the left, and basically nothing in nature is completely homogeneous. So we'll have some fluctuations coming from temperature differences, random fluctuations, quantum fluctuations, effects of other bodies in the sky and the surroundings. In some places, we can look at those fluctuations and ask, are they stable or unstable? That is, if we have some overdensity at some portion of the cloud, will that overdensity decrease? Will it just fade out into the rest of the cloud, disappear, dissipate? Or will it actually induce more mass to be attracted to the same overdensity and eventually cause a collapse? Now, unlike electromagnetism and electrostatics, there are no negative charges for mass. Mass is always positive. So naturally, if you have just at zero temperature, some mass overdensity somewhere, it will attract everything around it and it will grow. So at zero temperature, we expect every mass instability or density instability to be unstable, to grow and accumulate more matter if it's an overdensity. But nothing is at absolute zero in the universe either. And so we have to compare the actual temperature in the gas, which will determine its pressure and its kinetic energy, to how much potential energy or how deep the potential well is that forms around this overdensity of matter. So we'll use the Virial theorem, which we've mentioned before, and we'll compare two quantities. One is the kinetic energy, and one is the total energy. We remember that the total energy is mostly governed by the potential energy and the kinetic. If the potential is more negative than the kinetic is positive, then our system is trapped, it's confined, which means there is not enough kinetic energy for the elements to fly away from each other. They're closed and eventually they'll collapse together. If the kinetic energy is higher than the potential energy, then the system will disperse. Things are hot enough and they'll just fly away. The virial theorem tells us that the kinetic energy is in equilibrium on average minus half the potential energy. And so we'll compare the total energy, the sum of them, to twice the kinetic energy. Now we'll do some just order of magnitude calculations. If we have approximately constant density rho, then the radius goes like the cubic root of m over rho. That is, the total mass we can think of as 4 pi over 3 r cubed times rho, just the mass in a constant density sphere. So flipping rho to the other side and taking the cubed root, we can isolate r as a cubic root of the mass over rho. The higher the mass at the same density, obviously the bigger the cloud, the larger the radius. The higher the density, the smaller the cloud, the smaller the radius because it's denser. The potential energy goes like gm squared over r. There's a prefactor here which you can typically calculate, something like 3/5 or something like that, calculated the same way as you would in electrostatics for a charged sphere. You integrate from the inside to the outside spherical shells in spherical symmetry, calculate the potential, calculate the energy. And if we substitute in here the radius in terms of the density, we get that this grows with the mass at the power of 5/3 and grows more slowly with the density just to the power of 1/3, coming in from the radius in the denominator. The kinetic energy we can calculate through the temperature directly. We know that the temperature gives us the average energy per degree of freedom. That is 1/2 K Boltzmann's constant times T per degree of freedom in 3-dimensional space or a 3-dimensional gas, which we assume to be non-relativistic. These temperatures are typically low. Then we have 3/2 K Boltzmann T times N, which will be our number of particles or degrees of freedom per particle. And so we get that the average kinetic energy can be approximated by linearly in the mass, 3/2 m, K Boltzmann T, and we replaced here, or put in here to calculate the number of particles m by the mass divided by the same density. Only here we substitute the density in terms of physical, more accessible physical parameters, which are again the average atomic weight and in terms of the mass of hydrogen. Because yes, the basic unit of measurement is the most common massive particle, which is a proton or the nucleus of hydrogen. There are also electrons in the gas, whether it's ionized or not. Their number is approximately equal to the number of protons, but their mass is not really significant. So their effect will basically be to reducing mu to about half. If half of the particles have no mass and half of them have the mass of a proton, then the average mass per particle is about 1/2 the mass of a proton. Okay, so here we have, again, potential energy and kinetic energies, and we see that the temperature fits in and the density and the mass in different powers. So if we compare these two, we actually get a condition. We want the potential energy in absolute value, or the total energy in absolute value, that is the depth of the potential well, to be stronger than the kinetic energy. This will give us a condition relating the mass to the density and the temperature. And that criterion is called the Jeans criterion. It basically tells us that at a given temperature, density, and molecular or atomic composition mu, we have a minimum mass for such a perturbation to be bound, which makes it unstable. Above that mass, a cloud will collapse. Below that mass, a cloud will not collapse. It will have too high temperature, too high kinetic energy, and it will disperse. And basically, you can see that here, without going into all the numerical factors, temperature appears in the numerator. So as the temperature grows, there's more kinetic energy, so you need more mass to overcome it. Density appears in the denominator, because the denser the cloud is, that is, the more compact it is, the easier it is to collapse. You can overcome kinetic energy if you push the mass closer together. And so the threshold mass, which is the Jeans mass, is lower. So in terms of mass, we have this Jeans criterion for collapse. Given a temperature, composition, and density, you know which clouds will collapse and which will not. Alternatively, you can substitute again M in terms of rho and R and find a different type of condition. You can find the Jeans condition for the radius. That is, given, again, a temperature, composition, and density rho, what is the minimal size of the cloud that will be massive enough to collapse? So if you have an overdensity above this radius, it will collapse, it will be unstable, and you'll have again that a star is being born. Now, what that means is, in a typical huge cloud of gas floating in space, you might have no centers of nucleation. You might have no regions which are large enough to or heavy enough to cause this collapse. On the other hand, you might have multiple of them. You might have, if the gas is dense enough and widespread enough, or heavy enough and widespread enough, then you might actually see that this condition, making the cloud unstable, will actually have multiple different random points start to collapse simultaneously or close to each other. And then you'll have multiple seeds of stars and multiple protostars evolving together, as we see in this image here on the left. Multiple points of stars forming together. Eventually, these will form a cluster of stars that evolve together, are born together and evolve together in this stellar nursery or star-forming region. Plugging in typical... There was a question?
Yeah, you're basically saying that if we have a cluster of, inside the star nursery, we have a cluster, for example, in one part of the cloud gas, it has higher density. Then this part also only will collapse. It's not that for example, other gas now will collapse also to this new star that formed.
So if you can think of this radius as giving you you can think of an infinite cloud of gas or a very, very large cloud of gas. This radius is basically telling you the minimal size for perturbation or for an overdensity to collapse. So the same cloud can actually have multiple points, each collapsing to its own protostar and then its own star. But to collapse, this patch of gas will have to be larger than radius r. So if your cloud of gas has a typical density, which is high enough, or temperature which is low enough, it will be unstable, and multiple different points can collapse to stars simultaneously, or almost simultaneously. Whether two different patches will collapse on each other, you'd have to choose, you have to see if they're in the same, if relative to each other, they are free or bound, which is a slightly different condition. Okay. This is basically just saying that small perturbations or small overdensities will dissipate, but if they're significantly large, then they'll collapse. And if all of your cloud is over the density, then it might start collapsing at once, and then different patches might collapse even faster, and you might have multiple sites of nucleation and star formation and multiple protostars forming simultaneously while all bound to each other. and then you'll have a closed star cluster. That is, stars which don't necessarily hit each other, but revolve around each other and float around together in space.
So this criterion doesn't describe, for example, how do you call it, the dynamics of the systems, right?
No. This is no dynamics involved. This is just an order of magnitude criteria for understanding if the cloud is stable or unstable, or more accurately, what type of perturbations is it stable or unstable against? What is the minimal size of a perturbation which would collapse?
Okay.
If you look at the examples here, a molecular cloud of hydrogen, that's H2 molecules, has typically a temperature of about 10 Kelvin, which is where the molecules can actually form and be stable. If you have a typical mass of about 1,000 solar masses of hydrogen, molecular hydrogen floating around, with a typical density, which is density of these protostar clouds or nursery clouds. If you plug in the temperature and density and assume that it's all molecular hydrogen, you'll get that the gene's mass threshold is about 20 solar masses. If a typical cloud is 1,000 solar masses, then you understand that this is a very easy threshold to pass. And so that you'll have many nucleation sites, and this cloud will actually produce many, many stars in parallel. On the other hand, if you have an atomic hydrogen cloud, H1, here, the 1 refers to the ionization level, 1 means it's not ionized. So they're just atoms. These atoms typically have these clouds typically have a higher temperature, which is why the hydrogen is atomic and not molecular, order of 100 Kelvin, slightly less dense, but it's really the temperature that makes the difference. You see the temperature goes into the power of 3/2. So this factor of 10 in temperature will give a significant contribution to the gene's mass threshold. Here it will come out to about 900 solar masses. And because these typical clouds are smaller, only about 100 solar masses, they will typically not form a star. If you're exactly at the threshold, you need a more fine-tuned analysis to see exactly what type of perturbations you'd have, what type of fluctuations you have, which will collapse faster, which will collapse slower, and to kind of actually try to get a profile of how many stars you'll get and what masses will they have, depending on the exact initial conditions. And these are kind of simulations people do in galaxy formation and stellar formation and cosmological simulations, trying to understand exactly how stars are born, but this gives us an order of magnitude, how much mass and density you need for a cloud to start birthing stars. Okay? Okay. The process itself does not happen immediately. It does not happen fast in human terms. It is fast in astronomical terms. We mentioned before that we can calculate the free fall time of a cloud of gas. That is how long it would take a cloud of gas to collapse if it only had no pressure, nothing to oppose the collapse. So there's just conservation of energy here in the radial direction. So we have a radial velocity, and the change in radial velocity will come, or energy from the radial velocity, will come from the change in potential energy from some faraway distance, small r, to a closer one, big R, or vice versa, whichever way you want to think of it. In that case, you can find V as dr dt, and you have only R as the variable here. R is a function of time. Nothing opposes the collapse, so it's a straightforward calculation of calculating the integral over dr or dr dt, separating variables and integrating, and you get this order of magnitude time for the free fall of a cloud of mass. depending basically on G, gravity, which causes the collapse, and the density rho. And if you calculate this for something like the sun, with typical densities, you get that the free fall time is only about half an hour. So if the sun had no pressure, collapsing from an infinitely sized cloud to the sun would be very fast, only about half an hour. Of course, this doesn't happen. The sun is very hot, therefore has very high pressure, and this pressure opposes the collapse, which means that the actual time that it takes a star, a protostar, to contract while it heats up, while the pressure is building, until it reaches the size of a star and basically until it ignites hydrogen, is the Kelvin-Helmholtz time, which we mentioned when we talked 2 weeks ago, when we talked about the lifetime of the sun. This is the calculation that Lord Kelvin did when he thought that the source of energy of the sun was this gravitational contraction. So he divided the amount of energy available gravitationally by the luminosity of the sun and came up with this estimate relating how long a star can live, in his idea, based on converting gravitational energy to heat. This obviously doesn't happen once the star is producing its own energy from burning hydrogen, but it is a process that happens when the protostar, which is not yet burning nuclear fuel, is contracting against pressure. Contraction releases this potential energy into heat, into temperature, into pressure, and that slows the star down. And for the sun, it's about 30 million years, or the order here will be tens of millions of years. So the actual collapse of a protostar is a long process. And here we also have kind of an estimate of the Kelvin-Helmholtz time, or the time it would take a protostar to contract until ignition as a function of the mass of the star. That's on the left. On the right, this process, which is, as you can see, order of, can be tens of millions of years for stars like our sun, can be quicker for more massive stars because gravity is stronger, but still orders of tens of thousands, hundreds of thousands, and millions of years. That's the long duration of collapse. That's represented here in the diagram on the right bottom, or the lower right, on kind of an extension of the HR diagram, where we start in the corner with a very, very large cloud, which is very, very cold, so cold that it's on the outside of the HR diagram, far on the right. And because we remember that luminosity goes like temperature to the fourth, at very, very low temperature, it's also not very luminous. It outputs very little power, so it's on the bottom right. As it contracts and becomes, and forms this protostar, it both narrows down or condenses in radius while heating up. This heat is indicated by going up, going left in temperature and up in luminosity. And it's a rather mild heating process until the protostar is close and hot enough to induce convection. This is represented here with the turnover to phases 2 and 3. Convective processes spread the heat, as we saw, much faster. The star heats up more, condenses more, keeps turning left, so it keeps getting hotter and hotter, until eventually we have energy trapped in by different opacity processes. When different atoms can get ionized, opacity will grow, and so heat will be trapped in, the star will heat, and eventually ignite, here represented in circle 4, which is what we will from now on call not just main sequence, but zero-age main sequence, or ZAMS, Z-A-M-S, when the star is first born and appears on the main sequence. It has started to convert hydrogen into helium as a stable process, and now it has arrived on the main sequence and it begins its life on the main sequence. On the upper right, we see different types of zoom-ins of these final stages of the star approaching the main sequence, here going down in radius while maintaining constant temperature in the almost final stages until they make this final turn and reach the main sequence, the zero-age main sequence, igniting hydrogen. There's a lot more we could go into here for different stars and different processes. If anyone is interested in studying specifically birth of stars. For our purposes, this is enough for the beginning. Collapsing from a cloud of gas into a protostar, still condensing over a Kelvin-Helmholtz time until the temperature is hot enough to burn hydrogen. When does this hydrogen burning actually start? As we said in the first slide, we have brown dwarfs, which are failed stars. And above them, we have red dwarfs, and only above them, the actual main sequence begins. So again, the discriminating factor will be temperature, specifically core temperature, and whether it is hot enough to burn hydrogen into helium. So for these light stars, mass of the sun and lower, we can assume that they're fully convective. We can make other assumptions about the structure of the interior of the star and come up with this estimate for the core temperature, or the maximal core temperature, which is basically in the center of the star. In terms of solar masses, we see that it grows mildly, just over linearly with the mass of the star. And of course, it's determined by the chemical composition, the hydrogen to helium fractions, the electrons, so the nuclear properties, but mostly with the mass. Putting in the correct units and the correct numbers, we find a threshold of about order of tens of millions of Kelvin for stars slightly lighter than the sun. If we recall that the PP chain fusing hydrogen requires or kicks off at about 10 million Kelvin, then we need this factor here on the right to be about 10 million. So we need this factor of m over 1/10 m to be to the 4/3 to be about 1.5 or something like that. And this gives us a threshold mass, which is about 8% of one solar mass, or 80 times the mass of Jupiter. We're kind of pushing the red dwarf to brown dwarf limit, which is approaching the regime of planets. That is, stellar bodies which do not produce nuclear energy in a regular fashion. So you can think of Jupiter as being 1,000th of the mass of the sun. 8% of a solar mass is about 80 times Jupiter's mass. Things heavier than that will be hotter than that in the core, and they'll burn hydrogen into helium. Things lighter than that will not be able to stably burn hydrogen into helium, and then they'll either be very close to the limit. They'll be brown dwarfs. Below that, they'll just be planets. They will not produce nuclear energy. Okay, so again, the red dwarf threshold is about 8% of a solar mass. Below that, we have brown dwarfs, that is, failed stars, protostars which condensed enough to be gravitationally bound, but not enough to heat up and produce nuclear energy from hydrogen fusion. There are other milder nuclear processes which are easier to trigger, which can still take place below the official red dwarf line, so below the stellar line. For example, deuterium fusion. If you recall, the slowest process in the nuclear chain in our sun was the beginning of the PP chain, which was conversion of hydrogen into deuterium. That's mediated by the weak interaction, and absorb basically two protons interacting, while the weak interaction turns one of them into a neutron, forming the isotope deuterium. For that, you really need the 10 million Kelvin. But if you happen to have spare deuterium flying around in the gas cloud, you can actually fuse that with other deuteriums or with other hydrogens, even at lower temperatures. You don't need to overcome the big barrier that we talked about in the Gamow peak and the quantum tunneling and the repulsion that require this high temperature for HH burning. You can fuse deuterium even at lower temperatures, not a lot lower, but about 10 to the 6 Kelvin. So maybe a factor 10 lower than what you'd require for hydrogen burning. And if you plug this requirement, you get an order of magnitude almost reduction in the mass limit. And you find that already. Is there a question? Or? You find that already something like a star only 13 times as heavy as Jupiter can burn deuterium on its own. But this is a very short-lived process because there's not a lot of deuterium naturally present. Hydrogen and helium are the most common elements and isotopes in the universe. Deuterium is very rare, whatever leftover you have from the Big Bang or from other recycled stars. And it burns very fast because the temperature is lower and there's there's no requirement for the weak interaction to take place. So it's a fast process, there's little fuel of it. So this will run out very fast. So again, this is a failed star, a brown dwarf. It will not manage to live a life of burning hydrogen stably. Another process which can take place is burning lithium. This can happen already from about 3 million Kelvin. But again, lithium is very rare, so it won't last very long. You can also have kind of sporadic helium hydrogen burning if you use the deuterium burning energy to heat the star up, even if it's a light star or light brown dwarf, and use that to ignite the next step, ignite hydrogen. But again, it's not stable. As soon as the deuterium runs out, the process basically terminates. So all of these failed nuclear reaction chains can sustain energy for a very short time, but will not actually power a star stably. Below these limits, when you run out of these options, you're basically left with what today we would call a planet or a failed star. So brown dwarfs and lower, these are objects which are gravitationally bound, but do not produce energy from nuclear processes. Questions?
Yes. I was wondering if we go back to the first picture.
Which first picture?
The overview of the prostar to the...
Yes.
Where is like the type of stars, the normal Earth and the...
Earth is not a star. Earth is a planet. Jupiter is a planet. Earth is a planet. Everything that doesn't produce energy from nuclear burning is a planet. And as we just said, that comes at lower masses. Lower than about 80 Jupiters will be brown dwarfs around here. Lower than about 13 Jupiters will be supermassive planets, but they will not even be on this chart because they're too far down. They produce no nuclear energy, so in no way do we consider them to be stars. They're planets, they're bulks of mass, gassy or rocky, floating in space. They'll often form in star-forming regions because, for example, if you pass the Jeans mass limit, the Jeans criterion, you'll have an unstable cloud and it will start collapsing, but not all of the matter collapsing will necessarily reach the exact center, the seed. It will not necessarily reach the star. One of the reasons for this is that we only considered random motions from temperature, but we didn't consider specific motions like angular motions and angular momentum. Once you bring in angular momentum into the picture, you see that if a protostar that's collapsing, or a protostellar disk or cloud that is collapsing, has any angular momentum, net angular momentum relative to the center of nucleation, where the star will form, it's actually very hard to get rid of that angular momentum if you keep all the mass. And if you have angular momentum, obviously, the closer something comes to the center, to conserve angular momentum, it has to go faster and faster and faster. And so there's a barrier, which you can think of either the centrifugal force or an angular momentum barrier, which says that the cloud can't actually collapse all the way down because angular momentum will keep it flying outwards. The best way to overcome this is to separate the cloud or the protostellar region into multiple centers of nucleation, which will revolve around each other. At first, this will cause basically the cloud to turn into a pancake or a disk, to flatten out, the disk being perpendicular to the axis, which is the net angular momentum. So instead of having a cloud of random motions, at some point of the protostar, you'll have a protostellar disk, which is the center of the star, but gas swirling around in a disk around it rather than in a cloud. That's shown here. The spherical or three-dimensional cloud basically reduces to an almost two-dimensional disk. And this disk itself will be able to form nucleation of different elements, different objects. If they're large enough on their own, then you'll get another star and you can form a binary system of stars, a tight couple orbiting each other. If individually they're not large enough or massive enough, then they will not ignite nuclear fuel. They'll just be dead or inert, at least from the nuclear perspective. And then there'll be planets. And that's how solar systems are formed, where you have a star and the disk around it forms different clumps, eventually condensing into multiple planets. Mm-hmm. And the planets maintain the angular momentum of the original protostellar cloud, while most of the mass is in the central star.
I see, but planets do create a bit of energy, no? I mean, to sustain the stability of the planet itself from within the core.
Again?
But planets do have to have some kind of energy source from within the core to keep the stability of the planet.
Not necessarily. If a planet is small enough, then being small means that gravity is not strong. It's not very strong. Mm-hmm. So you don't need a lot of pressure to oppose gravity when gravity is weak. For example, if you think of an asteroid, which is basically a big rock, the pressure comes from electrostatic repulsion. It's the same pressure that keeps you from falling into the floor. It doesn't come from heat. It's not pressure that comes from the counterforce to gravity. Doesn't come from the floor being very, very hot and exciting pressure energy away. It comes from the ground being very, very rigid. So the electrostatic force is preventing you from sliding through it. And asteroids do this, and planets can do this. And planets can produce some energy. Our own Earth produces energy in the core, mostly from nuclear fission of uranium, potassium, and other trace radioactive elements. But that's completely insignificant relative to even to the energy that we receive from the sun 150 million kilometers away. Okay. So this can happen. Jupiter still produces energy from contraction. It's not completely stable gravitationally. It contracts very slightly, so it still undergoes, if you want, this kind of Kelvin-Helmholtz process. And all of these things can happen, but they produce very, very little energy compared to nuclear fusion. And so all of these things are not considered stars. They're just different processes that happen in planets or failed stars.
Okay, thank you.
Okay, so we mentioned before that stars are born, and they're officially born when they appear on the main sequence as zero-age main sequence stars. But the main sequence itself has some width and some dispersion, and this comes from two major reasons. One of them is that the chemical composition of a star changes throughout its lifetime. As hydrogen burns into helium, the fraction of hydrogen goes down, the fraction of helium goes up. So stars here are born as zero-age main sequence on this lower curve, here in mass and luminosity plot. But as they live, they will slightly go up in luminosity through over billions of years or whatever their lifetime is, depending on the mass. And this comes from the chemical composition changing, the density accordingly changes a little, the temperature changes. These are long processes which happen throughout a star's life and enrich or thicken the main sequence. Stars are born at zero-age main sequence, but then they kind of grow, they grow out of it, or they grow away from it ever so slowly. There's also, the second reason is original differences in chemical composition. Stars born today are no longer being born with the elemental ratios left over from the Big Bang, or from the primordial nucleosynthesis, because other stars have lived before them, conducted nuclear processes, died, and spread those elements around the universe. So our sun, for example, which is considered a population 1 star, that is the closest to us, is not a first-generation star. When it was born, it already had elements produced earlier in what we call population 2 stars, which came before. And so the chemical composition is different. And so this also gives kind of differences on the main sequence because of different chemical composition coming from when were these stars born. Population 1, which are now population 2, which is the older generation, or even possibly population 3 stars, which came even before that. Okay, I think this is a good time for a break. Next, we'll talk about the other side of the evolution, which is after all of this hydrogen was converted into helium, when the fuel runs out, how the star evolves after that. So let's take a break and continue at 1:05.
Okay.
And welcome back. So in the previous hour, we talked about how a cloud, typically hydrogen, mostly hydrogen, collapses to form a new star, to heat enough to ignite hydrogen in its core into helium, starting the life on the main sequence. Life on the main sequence can last for tens of millions, hundreds of millions, billions, tens of billions, even hundreds of billions of years, depending on the mass of the star, the luminosity, the energy output, and how long you have until the fuel runs out. The heavier stars will run out of fuel faster and live shorter. But eventually the fuel can run out, the hydrogen can run out at least. And we'll ask what happens then. So the first point to notice is that it's not necessarily all of the hydrogen in the star actually needs to run out for the star to stop burning. The main sequence life will typically end when only about 10% of the hydrogen in the full star has been converted into helium. And we have this kind of estimate, which depends on the chemical composition, of how much of the star is what we would consider the core. Again, from last week, The core of the star is that region which is hot enough and dense enough to actually undergo nuclear processes. So it's the part of the star where the luminosity is created, where the energy output comes from. Later, that energy, of course, dissipates, and it takes a long time, as we saw, to escape the star. But most of the energy is not produced near the surface, it's produced in the core. And what part of the mass, remember this is the mass parameter, of the star can be considered the core, is given by this relation of the core mass to the full star mass. And this is typically about something like 10%. So it's only enough to burn about 10% of the hydrogen available in a star for the core to become inert, that is, to remain with a helium core. If you have helium, you can no longer burn hydrogen into helium. There's no hydrogen left there. And then you'd have, again, no source of temperature and pressure, so nothing to oppose gravity. Or at least nothing significant to oppose gravity. You'd be leaving the regime of hydrostatic equilibrium. Again, it's not completely free fall because as the core now again collapses or condenses, it's not doing so freely. As it condenses, it releases more gravitational potential energy into kinetic and thermal energy. So the core is now reheating. It's heating again, now not by nuclear energy production, but by gravitational collapse. That heat again produces pressure, which opposes the collapse. But this is a much quicker process because the energy produced is much lower. You're not converting nuclear energy. You're only converting gravitational potential energy, and the star core is still quite big. This is not very significant. And so again, you have a Kelvin-Helmholtz process in a Kelvin-Helmholtz time. So the protostar took a Kelvin-Helmholtz time to collapse until it heated up enough to ignite hydrogen. Hydrogen ran out, you have a core of helium. Now the helium in another star again with a helium core can collapse again with a new Kelvin-Helmholtz time, not the same one. Now it will be the one appropriate for the new composition, the new mass, and the new radius. But now it will undergo a second phase of collapse. And the question is, what will that collapse lead to? And as always in stellar evolution, the answer will depend on the mass. So first we have red dwarfs. Red dwarfs, again, are the stars which are about half of the solar mass and below. So further to the right and down on the main sequence if you consider the age-jar diagram. And as we saw in the overview, and you can still see here behind me, below the sun, these red dwarf stars will never actually undergo will not change into anything else, will not run out of fuel, basically, for the duration of their lifetimes. They can live for about 100 billion years, so about 10 times longer than the estimate of the lifetime for our sun or stars like our sun. They're fully convective, which means they keep mixing new hydrogen into the core and removing helium out of the core as long as there are any available in the star. So they're actually very efficient in consuming hydrogen. But because they keep removing helium from the core never actually accumulates enough helium and never becomes dense enough to start to ignite the helium. The triple alpha process will never take place. So these stars only have one stage of nuclear burning in their lifetime, which is a very long lifetime, and that's only hydrogen burning. When the hydrogen runs out after 100 billion years or so, if the universe survives for that long, we're still iffish about the actual fate of the universe. If they survive long enough, then they can turn into white dwarfs or into brown dwarfs. Brown dwarfs is if they're small enough that they actually run out or drop below the conditions for burning hydrogen without having finished it all, just become too cold, and then they'll be again a retired star or a failed star. If they do exhaust their hydrogen, they will remain with basically just a full star, which is a helium, like a helium core, and that will turn into a white dwarf. And we'll talk later about what a white dwarf exactly is. Basically, it's when the pressure keeping the star from further collapse doesn't come from a hot gas, which is the hydrogen or helium. The gas is too cold because there's no nuclear processes. So the gas is not hot enough to produce enough pressure to stop the collapse. But there is something else which can stop the collapse, and that's the pressure coming from the electrons due to the Pauli exclusion principle, or if you want, the Heisenberg uncertainty principle. Electrons have to stay far enough apart in phase space, and so they will themselves occupy high enough momentum numbers or momentum states, and they will actually induce a quantum pressure which will keep the star from collapsing further. And we'll talk more about these white dwarfs later today. These are the mildest possible options for a star that's about half the mass of our sun or below. Easy retirement as either a cold brown dwarf or a white dwarf, which will then cool off forever. More massive stars, as we saw last week, don't have efficient convection between the core and the envelope. If they're like our sun, there's efficient convection in the envelope near the edge, but not in the core. So the core will run out and there will be no new supply of hydrogen coming in. If the star is much heavier than the sun, then there will be efficient convection in the core, but not in the envelope. So the core will recycle well and will exhaust all of its hydrogen, but again, nothing will come from outside inwards. So what that means is that when the hydrogen in the core runs out, there's again nothing left to produce nuclear energy, only gravity can produce energy, and so the core will contract. It will have a very low luminosity, which comes from it being inert, no nuclear processes. You can see this from this equation of stellar structure, in particular the temperature equation by luminosity. If the luminosity here on the right is taken to be 0, or so very, very small, effectively 0, then we have almost no temperature gradient, which means the core of these stars will be basically isothermal. The temperature will be almost constant. So we'll have a core of helium, which is at the same temperature and doesn't produce nuclear energy anymore. We might be in an intermediate situation where the heat from the core is still enough to ignite hydrogen around the core. So now we'll have a shell nuclear processes that is burning hydrogen to helium on a shell around the central core, not of course all the way out, but not in the core. The core is now inert, nothing happens there, but surrounding the core is a shell of, again, hydrogen burning. And this will add more helium to the core, this helium ash coming from the hydrogen burning. And this process can take a while. Releasing this energy as well, this heat, will cause the outer part of the star to expand. And this is typically what we would see as one of these transitions here. See? Transitions into a red giant. Okay, so a star like our sun will move to a red giant phase, which is burning helium instead of hydrogen and releasing that extra heat by expanding the envelope, the outer part. It actually produces, it works for less time, it's much less efficient process, but it will still convert hydrogen to helium around the core. If we manage to gather enough helium in the core and enough helium dense enough to actually heat the core and ignite the core, burning the helium itself in a triple alpha process, then we have a new phase of life for the star, the helium burning phase, or the helium fusing phase, which is very similar to the hydrogen burning phase, except that if you recall, helium burning is much less efficient. There's a lot less free energy or binding energy to produce from helium, even all the way up to iron, than there was from hydrogen going up to helium. If you recall the stability of isotopes and the binding energy per nucleon diagram plot. So there'll be a short phase of life of helium burning. And that phase itself, we can distinguish into two options. In the heavy stars, when the helium accumulates slowly, the temperature will build up slowly from the center outwards, and we'll have a gradual process of transitioning into burning helium. That's simple enough and close enough to a regular star, only burning helium instead of hydrogen. However, in stars like our sun of medium mass, the core of the star will actually not reach high enough temperature, this 100 million Kelvin for igniting helium. It will not actually happen so fast. What will happen is that you'll need a lot of helium to accumulate before the temperature rises enough, because the star is itself not heavy enough to produce the pressure. What will actually happen is that the core might become degenerate, that is almost like a white dwarf. It will be held together by electron degeneracy pressure and not by gas pressure, which means the temperature of the helium will again will be have very low luminosity, be almost isothermal, and all the helium in the core will basically be at the same temperature and rise slowly in temperature rather than rapidly rather than having a temperature gradient. What that means is that when eventually the core becomes hot enough and dense enough to ignite helium, it will happen not just in the center of the core, but all over the core, because the core is basically all at the same temperature. This is called a helium flash. It releases a lot of energy because you basically take approximately a solar mass or half a solar mass or something of the order of a lot of matter in the middle, in the core of the star, and you ignite it all at once. So you release, instead of a prolonged burning of helium into carbon and higher elements, which in a heavy star would take many, many, many centuries, thousands of years and above, millions of years. In a helium flash, it would happen very rapid. It would be a very rapid process, as a matter of minutes, hours, days, something like that. And so it's called a flash, releases a lot of energy very, very fast. Now, a question: if there's a helium flash in the middle of a star like our sun, what will happen to an observer on the Earth outside? What will we see? Any guesses?
I guess not all of the light we'll see. We'll see only some of it.
Why?
Because the light can escape. It will take him some time. It will not be instantaneously, but it will take time for it to escape.
Exactly. So as we saw last week, a star is typically very opaque, and it takes a very, very long time for photons released in the center to actually reach the surface and then the Earth. And as long as we still have this hydrogen envelope surrounding the stellar core, just because something happens and releases energy in a matter of hours in the center doesn't mean we'll see it in minutes, hours, or even years. Because if it takes 1 million years for an average photon to get out, then this energy might be released over hours, but it will take millions of years to actually propagate out and reach us. So the sun will heat and there'll be another process, but it itself will take a very long time. And I didn't mention this, but the red giant phase actually grows the sun to a very, very large giant. And the Earth itself is expected to be within the radius of the sun when it expands to a red giant. So it won't actually survive that long anyways. But if we were on Mars, for example, Mars is probably going to be safe. And if they wait long enough, they'll eventually see the energy coming out of this helium flash. What you can see directly from a helium flash, however, is a gravitational wave if it produces one, because as we'll see in about 3 or 4 weeks, gravitational waves, another form of radiation which is produced by astrophysical processes, is not stopped by these dispersion and scattering processes in the sun. Gravitational waves have a very, very small cross-section for interaction with matter. So they'll basically come out within seconds out of the sun. So you theoretically, if you could detect them, you could measure a helium flash happening deep within the sun about 1 million years before the first photons come out of it. So that's another thing to think about. Okay, so here we have a more detailed view of the life of a sun-like star going through this various red giant phase and helium flash stage. The star starts at time 0, which we name zero age main sequence. The sun grows in luminosity slightly over its entire lifetime on the main sequence, order of 10 or 12 billion years. And we said the chemical composition changes as there's more helium in the core, slowly accumulating from burning hydrogen. The core becomes slightly denser, slightly hotter, and so the efficiency of burning nuclear hydrogen grows. So the luminosity grows slightly over this long period until eventually the sun, the main sequence, grows into a red giant, eventually ignites helium. For our sun, it will be a brief process, a brief onset of a helium flash, and then remain in the horizontal branch, transition in the horizontal branch, and asymptotic giant branch, and go through various different types of thermal pulses as it basically runs out of fuel, reignites different types of flashes of helium until eventually it really runs out of fuel. The core is finally inert and there's nothing left to burn. At the end of the red giant phase, what you often remain with is just the core itself, which is by then a helium or carbon white dwarf. And the outer parts are just dispersed out into interstellar space as a planetary nebula. And that's basically what we expect our sun to do in about 7 or 8 billion years. Notice on this axis here that the rightmost parts are a lot faster than the left parts. So main sequence is order of 10 billion years. Then the entire red giant stages of life are only in order of a few 100 million years. So about at least 10 times shorter in duration. And eventually the final death of our sun is only a matter of a few tens of millions of years. Okay. That was just for a star like our sun. But of course, as we said, mass will determine what types of processes can happen in different stars. And stars that are heavier than our sun can survive the end of the helium burning stage. If they're hot enough, they can burn a new type of fuel. The helium produces carbon in the triple alpha process. Carbon can be burned into oxygen and nitrogen, and higher up, neon, silicon, all the way up to iron, depending on the mass of the star and how much temperature it can develop in its core. And so this is a typical plot from a book we put on the Moodle website, Eben's book of stellar evolution. This is just a 5 solar mass star, so not that much heavier, but we can see that it goes through many different types of processes on the HR diagram as it evolves through the main sequence, which is burning hydrogen in the core, later burning hydrogen in a shell around the core when the core is inert, developing into a red giant phase, igniting helium here at step 7, burning helium in the core, later possibly burning helium in a shell, and maybe later burning other types of fuel. So many different types of successions of fuel processes can happen in heavy stars. The more massive the star, the more stages it can go through. And we won't go into each and every one of these turning points or steps along the way. Just remember that in general, the phases where you burn a single fuel are the long ones. For example, the main sequence or the helium burning phase. Those can last for a very, very long time. For this star, the main sequence part is about 10 million years. The next stage, the core helium burning, as you can see, is only order of 1 million years. Sorry, 10 million years versus 17 million years. So there's an order of magnitude again between successive fuel burning stages, but the burning stages are long. What's quick are these transitions from one stage to another, or as we said, you run out of one type of fuel, there's no longer enough pressure to maintain the star in hydrostatic equilibrium, and then you have a shorter time scale, the Kelvin-Helmholtz time scale, during which the star readjusts, compresses, expands, turns into the next stage until again something ignites and you have hydrostatic equilibrium until that type of fuel runs out. And this can happen in succession with many different types of fuels. The fast stages then are the exchangement of fuels, the realignments. Igniting different types of fuels is fast. Convective stages can happen fast. And as we mentioned, the helium flash is fast, but generally stable burning of a nuclear fuel, whichever it is, will be a long process. Here we have a kind of summary from the same book from Iben of the evolutionary tracks by mass, so different masses of stars along the HR diagram. Our sun is here on the bottom, almost the bottom right, a 1 solar mass star. And as we said, it will evolve into a red giant, if you consider this as an HR diagram with temperature and luminosity. The low mass stars, the red dwarfs, never switch nuclear fuel. They just gradually burn out and die out. More massive stars will have different tracks, horizontal branches and other tracks. Here's the same 15 solar mass star, which changes a few nuclear fuel types, all of them climbing in different paths towards the up and right. So growing colder on the outside, but more luminous. So they basically become giants, red giants, asymptotic giants, and other types of giants. And this will today we understand this will explain stars that on the HR diagram will be towards the upper right corner or regions. The region of the main sequence is so thick along this diagonal, while the giant regions are very, very sparse. If we just look at the sky and count how many stars appear in different regions, is of course that the faster, the heavier giants, or the stages where you burn helium and where you spend in the giant branches and as a red giant, are much faster. In this table here, we see the different intervals related to this plot on the right. Again, ordered by mass of the star from bottom up. So you can compare directly to the diagram on the right, from our 1 solar mass star up to about 15 solar masses. And you can see that the main sequence, stages 1, 2, last for about 10 to the 7, half 10 to the 8, 10 to the 8, 10 to the 9, with our sun almost 10 to the 10, so almost 10 billion years. The number in parentheses in these plots, in these tables, is the exponent. So a very long time on the main sequence, and you can see that it's orders of magnitude longer than any of the times here on the right. So the next stage here, stage 2, 3 for our sun, will only be 2 billion years, then 1 billion years, 150 million years, etc., etc. As you go towards the right, that is, as evolution progresses, stages become quicker and they undergo stage transitions faster. So even if every star were to go through this entire process, looking at the sky, you would still see very few of them because they spend very, very short times in those late stages of their evolution. Questions up to now? Okay. So this again is the HR diagram. Now we can now we know not only this main sequence, main band here. Now we also understand some of these giants appearing on the right, giants that grow out of the main sequence as stars transition into their giant stages. And on the left, we have different types of stars found in a globular cluster. MS is the main sequence. And we have here different types of red giant branches, the red giant branch, the asymptotic giant branch, the horizontal branch, and different types of tracks for stellar evolution. And each point here represents an actual star observed in this cluster. And of course, almost all of them are along the main sequence, but you can see how different stages kind of peat out towards the upper right when you actually observe a cluster to include stars of different ages or different stages of their evolution. Another thing to notice here is that even the main sequence part is thicker and more dense towards the bottom right than towards the upper left. And the reason for that is the same. The heavier stars burn out faster, so spend less time on the main sequence and are observable for less time in general. And if you can actually up to the edge where you can't see them anymore, you'll expect more stars of lower masses just because they live a lot longer. It's a selection effect. Okay, so the really heavy stars, here given for a 25 solar mass star, which is now massive enough to actually undergo all the nuclear burning stages all the way to iron. What they will typically develop is this onion shape or onion structure, which is with density and temperature maximum at the center and decreasing towards the outside. As you remember, the Gamow peak, which determines if a nuclear process is possible, is very, very sensitive and narrow in the parameters of temperature and density. So you'll basically get disjoint shells of different nuclear processes burning from the inside to the outside. The middle will be, in the end, will be an iron core, which can't burn anymore. Out of that, you might still have silicon and sulfur burning into iron. Out of that, oxygen into silicon, carbon into neon and magnesium, helium into carbon and oxygen, etc., growing towards the outside. The heavier elements will sink downwards and accumulate or burn. The lighter elements will be near the outside. And if you look at the core, what is the actual dominating process at each stage of the evolution of the star, you can again see the same effect that we discussed before. Successively more advanced burning stages burn higher elements at much higher temperatures. The temperatures keep increasing with an increasing density, but the duration, the lifetime of that process gets shorter and shorter. A 25 solar mass star will live for less than 10 million years. For 70% of that time, or 90% of that time, it will be burning hydrogen. And then for the duration of its short life, will quickly go through helium, carbon, neon, oxygen. Silicon burning lasts for a day, and the final collapse when there's only iron and you can't burn anything anymore into a core collapse, bounce, and supernova will last seconds or even fractions of a second. And we'll talk about this particular part, the explosive part, again in a few weeks.
Perfect.
Yes.
I wanted to ask about the red giant.
Yes.
That we say that the red giants are created when we stop burning hydrogen because there's no more, and then we start burning helium, right?
Yes.
And does it expand because the helium doesn't give it enough force, or gives it too much force for the stability to remain the same, so it expands because the force outside is stronger than the force inside right now? So it gets...
So you actually have an exercise about that. I don't remember if it's in Yehu's tutorial or in the homework exercise that I put up today, but there's a question exactly about that to work it out. And in brief terms, what happens is that as the core contracts, it releases gravitational energy. Not all of that gravitational energy leaves as luminosity. A lot of it causes the outer part that's not collapsing to the core to expand. So it's a simultaneous readjustment of the star where the helium core becomes much denser and all the rest becomes much fluffier.
Okay.
And basically because if you consider the way in which the energy depends on mass, the potential is 1 over r, depends on the radius, 1 over r, making the core very small releases a lot of potential energy, which would then make, to maintain equilibrium, would cause the rest of the star, the outside, to get a lot bigger. So the core of the sun, for example, will be about a white dwarf size, which as we'll see is about order of 10,000 kilometers, causing the rest of the sun to expand basically to around the radius of the Earth, order of 100 or 200 million kilometers. So the core collapses, the rest expands.
Okay, I see. Thank you.
Any other questions? Okay. So what finally happens when all the fuel runs out? When you're out of hydrogen and then out of helium as well, or out of carbon, or at whichever stage that you stop. And we're going to be discussing at this point, first the non-explosive stages, not yet a supernova, just these regular stars here we see that live out their life, run out of fuel, and eventually leave, in most cases, a white dwarf. Oh, so we have it here as well. As we see, the explosive processes start for heavy stars around a blue supergiant in the HR diagram. Above those, we'll start having core collapses. So stars will die spectacularly with an explosion, with a core collapse supernova. But below that, for sun-like stars, even somewhat above the size of the sun, after the red giant phase, as we said, there will be finally a shedding of the outer part into a planetary nebula with a white dwarf remaining. For a red dwarf, it's even simpler. We'll have eventually a white dwarf remaining. So we actually expect most stars to finish their lives as white dwarfs. And so from the rest, most of the next hour or so, we'll talk about mostly white dwarfs. So what are these white dwarfs? The first thing to say, worth saying about white dwarfs is that we've actually seen them long before we understood them, which is quite typical in astrophysics. Sometimes it happens the other way with neutron stars and pulsars and things like that. But most things we actually see, don't know what they are, and it takes us a long time to explain them. And the first white dwarf was actually seen with a telescope in 1783 by Herschel himself. very famous astronomer. I think we mentioned his catalog before. And of course, he didn't know what the star is. At the time, he couldn't, it was before spectroscopy, so we couldn't understand the temperature or the relation of the temperature of the star to the flux and to the luminosity. He couldn't understand what the size of the star was. It might as well have been just a very, very far star, a star that's very far away and therefore appears very faint. But it was seen already in 1783, although they didn't know what it was. Even later in 1910, when they finally analyzed the spectrum in the Harvard College Observatory by all of your favorite friends, which you remember from spectroscopy, Williamina Fleming under Pickering and Russell, it just looked white. That is a type A spectrum, which we can see around here. Slightly, it looks a little hotter than the sun, not incredibly hot at the time, but it should have been, in that sense, it looked like a main sequence star. It has an A spectrum, but very, very, very faint, much fainter than the ones that we are used to seeing. Sirius B, which is a white dwarf, I think you might have seen either with Yehu in a tutorial or in a homework exercise. It's an interesting case because it was predicted before it was seen. It was predicted gravitationally by Friedrich Bessel, who basically noticed irregularities or wiggles in the position of Sirius, then just the star Sirius. Today, after we found Sirius B, the original Sirius is called Sirius A, which is a main sequence star, which appears here. And Sirius B was predicted by the gravitational effect on Sirius A and found about 18 years later. The first analysis of the spectrum of Sirius B, also said that it's basically similar to Sirius A. We can see both of them on the HR diagram on the left. Today, Sirius B is actually positioned a little to the left as a O-type star, somewhere between O and B, at least temperature-wise, while Sirius A is somewhere almost A. It's a B-type, almost A, so a high B-type. They're not exactly the same, but still we're talking about stars that appear generally white, but very, very dim, much dimmer, about, you can count 1, 2.5 times 2, so about 5 orders of magnitude dimmer or less luminous than the main sequence stars of the same color or spectral composition. And in the late 1910s, they started to understand or think of what these were and understand that they're actually a distinct population. Sirius B had a great role in this because unlike this Herschel star, 40 Eridani B, which was found as an individual star, and so you couldn't tell how far it was in the sky, we knew exactly how to compare Sirius B to a different star in the sky. Sirius B is gravitationally bound to Sirius A. They're one gravitational system. They're bound to each other. So even without knowing how far the system is in the sky, you know that both constituents must be at the same distance from us because they're basically close to each other. They're bound gravitationally to each other. They're a binary system. And this now enabled us to position Sirius B not only on the left-right axis by color, but also by comparing the luminosity to Sirius. And then we can obviously see that there is a very, very distinct population. No one can mistake these white dwarfs, if you know the distance, to a main sequence star. It's a distinct population of different types of stars. And of course, calculating the surface temperature from the spectral type and comparing it to the luminosity, you can easily calculate, and you've all done this already in this semester, that the radius has to be very, very small. Actually, about 100th of the radius of the sun, which means in volume, it's a millionth of the volume of the stars that we know. It's a star that's 1,000,000 times smaller in volume or 100 times smaller in radius. The mass of the sun as a white dwarf would be about the size of the Earth. So a lot smaller. And this is this kind of summary that Eddington, a famous astronomer, made in retrospect a few years later, saying that when we first discovered these stars and started analyzing them, their spectra and their luminosity, and it basically made absolutely no sense. How can you take a star hotter than the sun, but producing maybe 100th or 1,000th of the energy of the luminosity and condense it into 1,000,000th of the size? A very dense star, and we had no way of, at the time, of understanding how this thing could be. Today, we actually know many more of these. We know tens of thousands of white dwarfs already found just in our Milky Way. We expect that about 10% of the stars in the Milky Way should be white dwarfs, even at the present time. The reason we see fewer of them relatively to regular stars is, of course, because they're 100 or 1,000 times less luminous. So about 100 or 1,000 times less easy to spot in the sky. So we see much fewer of them, even though we expect about 10% of the population already to be white dwarfs. And because they are remnants of the relatively low mass stars, from the bare minimum of red dwarfs up to stars slightly more massive than the sun, we actually expect about 97% of stars in the Milky Way galaxy to end their lives as white dwarfs. So already today, about 10% of the stars in the galaxy are white dwarfs, and the other 87% of stars in the galaxy are expected to eventually turn into white dwarfs when they run out of nuclear fuel. So this is a very common type of star. Eventually, it will become maybe the most common type of star. Stars that have actually started nuclear burning will probably finish their lives as white dwarfs. Let's take another break until 2:04, and then do the heavy lifting part, which is the mathematics and quantum mechanics of actually holding together a white dwarf. Okay. I will say that I don't know how many of you follow the additional material we put on the Moodle website. Each week, we typically put a few links to other lectures, video clips, things like that you can find assistance or deeper understanding of, or just neat clips people did. There are actually 2 links we put on today's lecture in week 7. Videos by a group called Brilliant on YouTube. They have one for white dwarfs and one for neutron stars, which have no math in them at all, but explain some of the basic concepts, and they're neat. So you can always look at those as well. We're about to go into the mathy part. So first we'll say that there are actually more than one type of neutron star, of white dwarfs. We have the same classification of stars, the OBG, etc., OBAG stars. White dwarfs are specified under that same classification as D for dwarf. And the second letter will indicate the composition of the spectral lines absent or present in the atmosphere. And these typically indicate, or we can use them to infer, that different neutron stars the different white dwarfs actually have different compositions. Helium white dwarfs are, of course, as we said, things like what will remain from smaller stars when the hydrogen runs out and only helium remains. So the helium core will be a white dwarf core. If the helium got burnt into carbon or oxygen, we'll have carbon-oxygen neutrons, white dwarfs, carbon-oxygen white dwarfs, and heavier elements can have nitrogen or neon white dwarfs, and there are other types as well. Another observation we have of white dwarfs, which can help us understand their structure and kind of how weird they are, is of course spectral analysis. But here we're not going to be looking only at which lines are present and which lines are missing, but also at the width of the different lines. So for a typical spectrum here we have of our sun, and we see many, many sharp lines. In a white dwarf spectrum, okay, some of the lines are missing because we don't have the same elements, that's fine, or temperature, but that's fine. But you can notice that many of the lines are actually blurred. They become wider. And the reason is that the frequency becomes less accurate, less exact. The reason for that, as we've mentioned before, is basically Doppler shifting. Because the star is so much smaller and denser at approximately the same mass, that means that the gravitational potential is much deeper, which means the kinetic energy of the typical kinetic energy or pressure or velocities, each way you want to look at it, are much higher in the photosphere of the white dwarf, which means there are many different options for a Doppler shift. A particle can now emit or absorb, in this case, an absorption spectrum. It can absorb a photon not only in the exact energy it would have needed to in its rest frame, but it can either be moving towards or away from the incoming photon, have a redshift, and because this velocity dispersion is very wide because of the high gravity, these lines are blurred. So it can absorb photons and have an absorption spectrum in fewer lines, but wider ones. The opposite case happens in giant stars, which are very, very big. Hence, gravity is very, very weak, and then the lines are sharp. So another way that a spectrum can actually tell you about the relative size of the star, the gravity of the star, surface gravity. Okay, so how do these white dwarfs work? If we say that there's no nuclear energy production in the core, then the temperature in the core is not enough to sustain the pressure that will balance gravity, and the masses are typically still about 1 solar mass or 1/2 to 1 solar mass. So gravity is strong. Even more so, because as we said, the star is a lot denser. It's 100 times smaller in radius than our sun. So the gravitational force will be 10,000 times, 100 squared times stronger. If gravity is that strong, we need a very high pressure to balance it, but we can't produce that pressure from heating the gas because there is nothing to heat the gas. There's no energy production in the core. The core is small. Small, dense, but not exceedingly hot. What then can block this collapse, this gravitational collapse? What can stand in the way of gravity? What pressure will be there to prevent the gravitational collapse? And the answer given in 1926 by Fowler was degeneracy pressure. Degeneracy, you might recognize the word from studies in quantum mechanics, is when we have many different particles occupying similar energy states or phase space states, or having different options in phase space for the same types of particles. This is basically the name that this phenomenon has received in astrophysics. Basically, it comes from the Pauli exclusion principle, which Pauli first came up with and published the year before. And what it says is that if there's a limit to how much you can compactify or push together particles, which are what today we would call fermions. So fractional half-spin particles, as opposed to integer spin like photons, which are bosons. Fermions cannot occupy the same quantum state, identical fermions. That means for each fermion that you add, you need a new state a new vacant state able to receive it. how many states will you require? The number of fermions, particles that you have. So per unit volume, you'd have the number density of particles, fermions of a particular species. And what you'll do is you'll be using the Aufbau principle, which we mentioned in week 3. You'll be filling up energy states from the bottom up. The first fermion at the low temperature, if the temperature is low enough, we'll just assume it's 0 relative to what we're discussing. And at 0 temperature, the first fermion will occupy the ground state. The next fermion will occupy the next state available, and up and up and up and up until you reach the top level, which would be called the Fermi level, determined by how many particles you have that need to be housed somewhere. So if we look at this plot here on the right, this analogy of a plot, we can think of this plot as describing phase space. Phase space is a product of position space, represented here by the horizontal axis x, and momentum space, here represented in the vertical axis p. In this case, it's represented as one-dimensional x and p. In reality, they'll be both be three-dimensional. If the potential is independent of the position, which is a fair assumption to make, we have some core with some relevant potential, but it doesn't change very much with position, then basically the energy will be determined by the kinetic part, which is the momentum. So higher momentum will indicate higher total energy. That means if we have this if we throw away a bunch of particles, fermions, in this case, maybe electrons, into this region, they'll start filling up phase space one by one by filling up these squares from the bottom up. The first batch will fill up the bottom line, then the next line up, the next line, and in this case we have 1, 2, 3, 4, 5, 6, 7, 28 particles here, occupying 28 squares or slots in phase space. Each slot is basically given by the volume in phase space, which is delta x delta p, which you can think of as coming from the Heisenberg uncertainty principle. Delta x delta p must be greater than h or h bar, in whichever form you prefer to look at it. Or with the Pauli exclusion principle, is basically saying that two quantum states cannot come closer in phase space than this elementary Planck volume h. So we basically divide all of our phase space into boxes of area h in 1D or volume h cubed in 3D, and we fill them up from the bottom up until the highest level, which be the Fermi level, here represented as PF, so the Fermi momentum. When the density is low enough, we can take the classical, that is non-relativistic approximation. Velocity is just linear in momentum, or momentum divided by mass. So the highest velocity particle will have the Fermi momentum divided by the mass m of the particle. The Fermi energy will be just a kinetic energy, so 1/2 mv squared, or in terms of the momentum, Fermi momentum squared divided by 2m. We can translate this kinetic energy into an effective temperature, asking what would have been the temperature of a gas of those particles so that they would have this energy. And we do that by dividing by the Boltzmann constant. If you want, you can add a factor of 3/2 or any other numerical constant, but the order of magnitude is basically E divided by K Boltzmann gives you the Fermi temperature T. That tells you that the temperature, the Fermi temperature for a species grows quadratically in the Fermi momentum and grows and diminishes linearly with the mass. It goes like one divided by the mass. That means that the lightest particles will have the highest temperature the highest velocities, the highest pressure, the highest effective energy, and the highest effective temperature. So in a star, like a white dwarf, if it's hot enough to ionize helium and hydrogen, which it typically is, then we'll have basically two types of particles in the core in the white dwarf. We will have nucleons, either nuclei of atoms, either hydrogen, helium, carbon, oxygen, etc. And we'll have electrons. The lightest nucleus is about 2,000 times heavier than an electron. So obviously the temperature will be determined and the pressure will be determined by the electrons. The lighter particles dominate. So in this case, in a white dwarf where we have electrons available, they will be determining the temperature, the Fermi temperature, the Fermi momentum, the Fermi energy, and it will be as if our core actually has two different populations of particles. It has nuclei, which are cold and have little pressure, but that will be dominated by the free electrons, which will basically have pressure as if they were at the Fermi temperature. And they can be much, much hotter, about 2,000 times even hotter than the nuclei. A very similar thing happens in ordinary conditions in metals in solid state physics, and Yehu will talk about that more in the tutorial, where basically you can hold a bar of iron or gold or anything like that in your hand at a temperature of about 300 Kelvin, but the electrons in that bar of metal, the fastest ones at the Fermi level, the Fermi velocity and Fermi temperature, will actually be equivalent to maybe 10,000 or even more, maybe 100,000 degrees Kelvin. And they'll be traveling at maybe almost 1% of the speed of light inside the metal bar in your hand, not because someone heated it, but because the Fermi exclusion, the Pauli exclusion principle, forces them to very, very high momentum levels or quantum states. Any questions before we do the actual calculation?
I didn't really understand it too well. Like the degeneracy pressure.
It basically goes like this. Say you have 28 electrons to put in this phase space on the right. At zero temperature, there's no temperature. This is representing a piece of metal that you keep in the refrigerator at zero temperature. What will be the velocity of the electrons? It will not be zero, because you can't have 28 electrons at the same velocity, which is zero. In this case, you will divide your phase space. So X will be the length of the metal bar. In this case, let's say it's the length of 7. And there'll be a height. The height is basically unlimited because you divide it up into boxes of delta P in height. Delta X times delta P is the volume you need in phase space, or the area in phase space that you need for a single quantum state. So if you have 28 electrons that you need to now house in this metal bar in position and momentum space, you'll start by putting 7 electrons on the bottom row. So you'll have 1, 2, 3, 4, 5, 6, 7 electrons. And they're all at energy zero. Effectively, they're at the ground level. That you can still do. But what happened to electron number 8, the 8th electron? You can't put it at momentum zero anymore, because all of the momentum zero states or slots are occupied And an electron is a fermion. You can't have two at the same quantum state. So even though the temperature is 0 in the refrigerator, you can think of it as saying that the metal bar is in equilibrium with a heat bath at temperature 0 or 1 degree, something very, very low. But that doesn't matter because you can't put the electron at energy 0. There's no room for it, it's occupied. You'll have to put them in the second row up. So it will have some positive momentum. Actually, the electrons 8 to 14 will occupy the second level, and they'll have a momentum of, in this case, Planck's constant h divided by delta x, however close you put them in the x axis. Electron number 15 won't even have space in phase space in the first two rows. It will go into the third row. And electron 22 will need to occupy the fourth row. So you'll actually have 7 electrons here, electrons 22 to 28, which will all be moving around quite fast. They'll have four quanta of momentum in this language. There'll be 4th level up in momentum. They'll be moving very fast. And you can translate that motion, that velocity, into kinetic energy and into temperature. And that temperature will be much higher than the temperature of the metal bar or of the refrigerator. And in a star, those electrons moving around will also create pressure. And that pressure can be strong enough if the star is dense to hold up against gravity. And now we also understand why it happens in dense stars, like in white dwarfs. Because as you shrink the star, you reduce the X options, right? You make X smaller. So you need, if you take this diagram on the right, if you squeeze it on the X axis, you'll be pushing the electrons up on the P axis. You'll be pushing them to higher velocities, higher momenta, and higher temperatures, hence higher pressure.
I see.
So a white dwarf is exactly this. It's when you condense the mass of the sun into the space of the Earth, and then you force electrons to go higher up until they no longer can actually be free from each other. They start repelling each other with this Pauli exclusion principle. They force each other up in momentum.
So we have a very high kinetic energy electrons which produce high temperature. Eventually.
Yes, so the electrons will be pushed into a high kinetic energy.
Okay. Thank you.
And now we can do the calculation. And the calculation is, we'll take the easiest simplifying assumptions that we can think of. Star of mass m and radius r, which means we'll take a typical density, rho, which is m over r cubed. I ignored factors of 4 pi over 3. As I'll do along this calculation, everything will be with tildes because I'm basically ignoring all of the constant numerical factors. So we have a typical density of mass. We can convert that into a number density to know how many electrons we have, how many states we need, by calculating the number density Ne of electrons as rho divided by the mass of a proton times the average atomic mass per electron. Again, how do I convert mass density to number density? I divide by the average mass of each particle. Then I convert density of mass to density of particles. And I'm interested in electrons, so I'll ask what is the typical mass of useful in atomic physics? It'll be the mass of a proton or the mass of a hydrogen nucleus or atom, but I'll have some ratio that basically only half of my particles have that mass. The electrons themselves are almost negligible in mass, but to count them, I'll count that each electron came from a proton. So the number is about 1 to 1. And so I have about a factor of 2 for this mu factor, average atomic mass per electron. Okay, what then is the Pauli exclusion principle telling me? It's telling me that if I have to find space in phase space for NE electrons, capital N electrons, that is number density small n times space volume V, that's the total number of electrons I need to find, n. I need to find a place for n electrons, so I need n quantum states for electrons. How many states do I have? Well, each electron occupies some place in position space, so that's the same volume V. It occupies some position or some place in momentum space, so that's the volume of momentum, Vp. In the diagram before, V is the x-axis and Vp is the p-axis. Only here it's not x and p, but V and Vp because it's three-dimensional. So my volume is V times Vp divided by Planck's constant cubed because the volume of each quantum state in three-dimensional space, phase space is h cubed. That is 1 h bar for every dimension. And this factor of 2, which very soon I'll ignore because it's just a numerical factor, comes from spin. It's because actually at each position and momentum, I can put not 1 electron, but 2 electrons if they have opposite spins. Okay, so this is telling me, giving me an equation. I see that the V immediately cancels out from both sides. So it's giving me n, small ne, the number density of electrons, equals 2 momentum space volume divided by Planck's constant cubed. What is the momentum space volume? Well, it's 4 pi over 3 Fermi's momentum cubed, because that's the volume of a sphere in momentum space with radius pf, the Fermi momentum. And I'm ignoring the 4 pi over 3. And so I get that Ne goes like p to the cubed divided by h bar to the cubed. So I take the cubic root of both sides, and I get that my Fermi momentum is proportional to Planck's constant h bar times the cubic root of the number density. And you can see that this makes sense in 2 ways. One, number density has units of 1 over meter cubed. If I take the cubic root, this is 1 over meter. So I have Planck's constant in units of angular momentum divided by length, I get momentum. So the units work out, the dimensions are fine. And another way to think of it is that as you increase the number density, the more particles you want to put in the same volume of space, that is, the more electrons you pour into this pool that we had in the previous diagram, the higher they will have to climb in momentum, because you need to find more phase space options, in this case, momentum space options, for more electrons per unit volume. This immediately gives me the Fermi energy, or the kinetic energy of my highest level electrons, as p squared over 2 me, the mass of the electron. So I get h bar squared, number density of electrons to the 2/3 power, divided by me, and I again ignore the factor of 2. What's the pressure? Well, if I have energy per electron Ek, then the pressure will basically be energy per unit volume, right? Energy is force per unit area, which is equivalent to energy per unit volume. Or if you want to think of it differently, you can use the ideal gas law, but be careful. In this case, I'm using the ideal gas law for a degenerate gas as an estimate. So I have the density n times Boltzmann's constant times T. Or if you want, K Boltzmann T is basically the average kinetic energy per electron. So I'm going to put that in as well. You can again check the units. This is just energy per unit volume, because N is in units of dimensions of 1 per volume. And of course, the more particles I have, the higher pressure. The pressure will be linear in the number of particles times the energy average per each particle. And substituting my average energy, EK, I get that P goes like h bar cubed, fine, that's a physical constant, times the number density of electrons to the power of 5/3. 2/3 come from the energy per electron, and another 1 comes from the density of electrons, divided by the mass of each electron. Lo and behold, this is an example of an analytically derived polytropic equation of state. This is a polytope. P goes like some constant times N or rho, the density, to some power, right? This power is exactly the adiabatic index, which in this case is 5/3, and it matches a polytropic index N of 3/2, which we had mentioned, I think last week, different types of polytopes. So here we have an example of an analytically derived polytope with a polytropic index of 3/2. Okay, so I now know the pressure of my degenerate electron gas in my white dwarf. I need to find out if this pressure is enough to balance gravity. The equation that compares pressure to gravity is the equation of hydrostatic equilibrium, which we saw last week, which says that if I have a piece of mass, an element of mass rho, the gravitational force it will feel is gm rho over r squared, with m and rho up to the position. So here we're looking at, for example, the edge of the core as a kind of typical value. And this will basically have to be equal to the gradient of the pressure. Remember, the gradient of the pressure is what balances out gravity. And I can approximate the gradient of the pressure by P over R. So if the pressure goes from 0 to some maximal value over a distance R, then an estimate for the pressure will be P over R. So now all I have to do is substitute rho on the left-hand side and substitute P on the right-hand side. And I get from my hydrostatic equilibrium equation that if my typical density rho is another m over r cubed, then the left-hand side gives me g m squared over r to the 5th. I had an m over r squared. I'm adding another m over r cubed. So m squared over r to the 5th. And on the right-hand side, I have my pressure, which is given here, divided by r. So I just copy it. I put my Planck constant squared. I substitute for n my expression, which was dependent on the mass and density. So density divided by average mass per particle, per electron. And the density itself, again, in terms of m and r. And I get this equation here on the right. And this might seem complicated, but all I did is exactly here on one slide. I just took some fiducial values, typical values, substituted them in, and I get an equation which has a bunch of physical constants: g, Planck's constant, the mass of a proton, the mass of the electron, the average mass per electron, which is dependent on the composition of my star, and two variables that I did not know, m and r. I only have one equation for two variables, so I can't solve both of them, but I can find the relation. If I move all the r's to one side and all the m's to the other side, I can count. Here I have on the right side r cubed to the 5/3 power is r to the 5th. It's in the denominator, and there's another r in the denominator. So there's r to the -6 total on the right side, and r to the -5 on the left side. So overall, all I have here is, if I multiply to the right, to the left, I'll have one r on the left side. If I collect my masses to the right side, I have m to the 5/3 in the numerator divided by m squared. So I'll have m to the minus 1/3. So my radius for a white dwarf is m to the minus 1/3 times gathering together all of the other constants which I had. And as we see here, the higher the mass of the white dwarf, actually the denser, the smaller it actually gets. If you add more mass, there's more gravitational pressure, so it pushes inwards, and so the star actually becomes smaller. Okay, this is the mass-radius relation for a white dwarf from analytical arguments and physical constants. This is basically the heaviest calculation we have today. So, any questions? Okay. Let's take some typical values, again, to see what we're dealing with. So we have our relation that says that a higher mass induces a smaller radius because there's an inverse relation here with a factor of minus 1/3 in the exponent. If we take one solar mass of white dwarf material, and as we said, we take mu e, the average atomic mass per electron, to be 2, then we can just put in all the numbers. Solar mass is 2 times 10 to the 30 kilograms. Planck's constant, 1 times 10 to the minus 34. It will be squared with the proper MKS units. I'm putting G in here, 6.7 10 to the minus 11 in MKS units. The mass of the proton, 1.7 10 to the minus 27. This 2 here is the mu e, the relative average atomic mass per electron. And the mass of the electron, 9 times 10 to the minus 31. This is just arithmetic. I can find first that all of my units, indeed, all my dimensional units cancel out. I'm just left with one surplus meter. And if I take all the orders of magnitudes here, they come out. I have some big numbers, I have some small numbers, but the arithmetic basically in the end gives me 0.002 10 to the 9 meters, or in more accessible units, an order of 2,000 kilometers. I remind you the radius of the Earth is about 6,000 kilometers. The radius of the Sun is about 700,000 kilometers. So a white dwarf in the mass of the Sun will be order of magnitude, I ignored a lot of factors on the way, orders of magnitude about the size of the Earth. And now we understand how it appears so low on the HR diagram. 100 times lower in radius than the Sun at the same mass. And equivalently, a lot denser, because if the radius is 100 times smaller at the same mass, then density is 100 times cubed or 1,000,000 times denser. And if we consider typical densities, then for the Sun, it's on average about 1.4 grams per cubic centimeter, just denser than water. The core is about 100 times denser than that, about 150 grams per cubic centimeter. But white dwarf densities can actually come to 10,000 even until 10 billion grams per cubic centimeters. So much, much denser, depending on their mass, which will determine their radius, much, much denser than the Sun or than anything we know from everyday life. There's a typical numbers given here on the right for how the density of a white dwarf can change quite a lot, or over 6 orders of magnitude. That, of course, relates to changing the mass and the radius. And we see here that white dwarf about the mass of the Sun, here about 1, we see is about almost 200 times smaller than the Sun, or 200 times smaller in radius, in units of the solar radius. If we decrease the mass, the radius actually grows. It's an inverse relation, as we just saw. And we can increase the density, And we see that, of course, the radius gets even smaller and smaller. Another 2 points to remember are that if the star gets a lot smaller, the angular momentum is typically conserved, and the magnetic flux is typically conserved. And both of them depend on the size. In the following way, if I reduce the radius of the star, then I'm reducing R. And if I want to maintain omega squared R, which is the angular momentum, by reducing R, I have to increase omega. So that means that these neutron white dwarfs will actually spin a lot faster than the original star. I'm increasing the rotational velocity because I'm decreasing the size. This is exactly what you do in first year mechanics, or if a ballerina closes its arms, it will spin faster. To conserve magnetic flux, which goes like BR squared, R squared for the area determining the flux, and B, typical magnetic field strength. If I reduce R, I have to increase B by that factor squared to maintain the same flux. So magnetic fields will also grow a lot when I shrink a star into a white dwarf. So 2 things to keep in mind. And the last one is that because these white dwarfs have such low luminosity, it will take them a very, very long aeons and aeons to cool off, longer than the time a red dwarf will burn, longer than, by orders of magnitude, longer than the age of the universe until now, and in the foreseeable future for a very long time, in orders of magnitude. Okay. The last thing we'll do today, the next to last, is talk about a limit to this mass radius relation. Because whenever we have the situation that as the mass grows, the radius shrinks, that means that the density grows. If the density grows, our electrons will start moving faster and faster. And eventually, our approximation of the kinetic energy being non-relativistic or classical, p squared over 2m, will break. When the electrons become relativistic, we have to switch to the relativistic energy momentum relation, which, as you might recall, is the same as the one for photons. E goes like PC, or which is the Compton relation, right? E equals PC. The problem is that if our momentum goes like n to the third root times c and h, I'm ignoring the physics here, the physical constants, it means that the degeneracy pressure now has a different dependence on density. Because taken as before, I take the pressure as the density times energy per particle. If the energy is now density to the third and not to the 2/3, I get that pressure goes like density to the 4/3. That is still a polytropic equation, but with a different index. Now I have a polytropic index of 3 or adiabatic index of 4/3, a different type of polytrope. And if I try to calculate now a mass radius relation with the same hydrostatic equilibrium equation, which I just copied from before, if you remember, the important part that I looked at was the power of R, which before appeared as R cubed to the 5/3, so R to the -5, divided by R gave me an excess R relative to the left side. But now the power is only 4/3 because the polytropic index, the adiabatic index is 4/3. So R cubed to the 4/3 is R to the -4 in the denominator, with the other R from the derivative gives me R to the -5, which means both the left side, the gravity side, and the right side, the pressure gradient, have an R to the -5 behavior, which means R cancels out and there's no solution. I can't actually find a solution for R that will give me a stable star in this case. Okay, if you want, you can think of it in a different way. You'll find an equation for M, but not an equation for R. But that doesn't matter. There's no R in which the star can be stable and satisfy hydrostatic equilibrium. That means that I'm actually not allowed to have white dwarfs dense enough to push electrons to relativistic velocities. That itself will cause the star to be unstable and collapse or explode. Which means there's an upper limit on the mass I can give a white dwarf and expect it to hold. What is that limit? Okay, so if I want electrons to be non-relativistic, I'm going to put the limit at the point where they become relativistic, which is approximately when the kinetic energy is of the order of the mass energy, of the rest mass energy. So E kinetic is approximately equal to E0, E naught, or the rest mass energy. In other words, I'm equating the classical momentum, P squared over 2M, to the rest mass in relativity, which is mc squared. Now just some math, I'm flipping m to the right side to get m squared c squared. I'm replacing the momentum by the density. We recall that Pf went like h bar n to the cubic root. So squared, it will be h bar squared ne to the 2/3. I'll take the the square root, I'm sorry, I'll take the cube and then the square root of this equation and replace my density with the parameters of the star, mr, and the chemical composition. And I'll get that m over r to the cubed has to go like this constant value. Notice that the right-hand side here has absolutely no star-dependent properties. It's just constants of nature. Proton mass, electron mass, velocity of light, Planck's constant, okay, and chemical composition, which we took to be just a factor of 2. So this relation is very strongly constrained, and it's not the only constraint, because we just had that if the star is stable, there's a relation between radius and mass. So I'll plug that in as well. I'll use that relation, and I'll find that I can isolate R and remove it, and have in the end an equation only for M. A little more algebra, which is not critical, but you can follow it if you want. We find that this limiting mass, the edge of the allowed range of white dwarfs, is given by this combination of physical constants, Planck's constant, velocity of light, g from gravity, divided by the composition, proton mass, and average atomic mass per electron. So this is just a combination of purely physical constants, and they determine the limit on a possible white dwarf mass. If you calculate it, it comes to about 1.4 solar masses, derived entirely from analytical arguments. Any questions? Okay, if not, then I'll just finish on this slide. This is a different derivation of the same thing by Chandrasekhar, Subramanian and Chandrasekhar. The limit is actually named after him, the Chandrasekhar mass. And again, he compares the limit of slow electrons, which is a polytrope with index 3/2, to the ultra-relativistic electrons, which have a polytrope of n equals 3. He actually plots or gives an estimate of the middle, the transition between the slow and ultra-relativistic regimes. We just took them as separate and put some random place in the middle. He did the calculation more accurately by doing some harmonic average of the pressure contributions between those two polytropes. Plotting his combination between them, he could trace what the maximal mass would be. That is, the non-relativistic Fermi gas will be this blue curve here that goes like r to the minus 3. The relativistic one will terminate at the transition and of the auto-relativistic limit, where the radius is completely undetermined by the mass, and the mass itself has to be a constant. And so we have that as the gas heats up and becomes more relativistic, it turns from the classical case, the blue one, to the auto-relativistic case along the green curve, finally reaching Cm, the Chandrasekhar mass, at 1.4 or 1.45, depending on how accurate you want it to be, solar masses. The Chandrasekhar mass, the limit on a white dwarf mass, the limit on holding electrons together densely in hydrostatic equilibrium with degeneracy pressure. Any questions?
Why did he define the limit that way, that the kinetic energy is equal to the resting mass energy?
So there are two ways to think about it. There's the Landau way and the Chandrasekhar way. The Landau way is order of magnitude. You don't expect a perfectly correct number, but get an estimate. And the estimate will say that when would you consider a particle as non-relativistic? When the kinetic energy is much lower than the rest mass. When would you consider a particle to be auto-relativistic? When the kinetic energy is much more than the rest mass. So the transition, I don't know if it will be at 0.1 E naught, 10 times E naught, 1.5. I don't know the exact number. It's not well defined. It's an order of magnitude calculation. But the relevant scale to compare to is the rest mass energy. So we'll get an order of magnitude estimate by making those two numbers equal. The Chandrasekhar method is saying, okay, I don't want to take just a guess of the intermediate part. I'll actually work out the full relation going from one to another. My pressure will be a harmonic average, or kind of a harmonic average of both contributions, the 4/3 polytope and the 5/3 polytope, with different prefactors you can calculate from the atomic physics. If you don't throw away all the factors of 4 pi that like I did, you can find the actual numbers. And then you can trace the pressure. And if you have the pressure, then you can calculate the actual pressure gradient, compare it to gravity, and solve this green curve, which is radius as a function of mass. Not surprisingly, at the very low end, it coincides with the non-relativistic limit. At the very high end, it reaches the auto-relativistic limit, which is radius independent of mass, not a stable star. If you're actually interested in a specific white dwarf, you'd need the green curve to know exactly the mass radius relation. It would be the green one. But if you're only interested at the limit, then you see that the limit, you can just ignore the prefactors and look at where the auto-relativistic case terminates.
Okay, thank you.
Okay, I had 3 more or a couple more slides about neutron stars. I'll just say that neutron stars are kind of like white dwarfs, only much harder to produce. We'll have when we talk about supernovae, we'll talk about creating neutron stars. The difference between them is that they're denser than neutron stars, and so you can't sustain them with electron degeneracy pressure. You actually replace the electrons and protons, combine them into neutrons. Then your star is only made of neutrons. Because the particles are heavier, neutrons instead of electrons, about 2,000 times heavier, then the temperature is lower, and so you can actually get a smaller radius and possibly a higher terminal mass. The exact calculation is difficult, and I think we left it for you as a homework exercise, basically repeating the Landau calculation, but replacing the correct masses between electrons and neutrons, and keeping maybe keeping track of a few more factors to find out what this higher mass is and what the radius is. And it comes out to be about 1,000 times smaller than a white dwarf, only about 10 to 20 kilometers for a solar mass. Okay, I think we'll stop here. Any more questions? We're going to leave this on just for fun. Basically, this is saying what we said in the beginning, how different masses will determine the final end state of a star. We'll talk about this plot and the previous one that I did mention again in a few weeks when we talk about supernovae and the actual death of massive stars. Okay, I'm stopping the recording now.